as mentioned a few seconds ago, my name is Jiří Činčura. Today I will be talking about most common mistakes in task, in using tasks and in asynchronous code. Well, there is a recording, so you probably don't need the presentation or the code, but even if you would, it will be sooner or later on my blog, which is tabsoverspaces.com, because we are developers and tabs are better than spaces. As I said before, if you have questions, write it in the chat, and I will try to answer as much as possible in the second half, or actually it's a third, the last 30 minutes basically, and we will see how far we get. So if you want to follow me or get in touch or something, probably the easiest one to follow what I'm doing and what interesting or not interesting stuff I'm playing with is my Twitter, which you can see on the screen. So give me a follow and you can see what I'm working on. So without any extra talking, let's jump into the presentation, and let's first start with thinking why actually we need an asynchronous code. Why do we care? So we can think about it from different views. The first one would be that you want to offload some kind of work from basically the UI thread, because that's the most common way of seeing that something is being blocked. Because as you probably know, not all threads are being equal, which means if you have a UI thread, you probably don't want the UI thread to be blocked, because if you block the UI thread, the users see that your application is basically frozen, and that's not a good experience, because he or she wants to click a button or minimize or move the window or something like that, and the application is not responding. And this is basically because you can see the latency in the client-side application. The other one is concurrency, because if you are not doing everything in one thread, in the UI thread, you can actually do multiple operations at once. And that means you can utilize your hardware a little bit better. So if we are talking about a network, you can actually use all the bandwidth you have available. If we are talking about your disk, the disks have a bunch of algorithms to speed up the processing of your reads or writes, for example, the native command queuing and so on. And the last, but definitely not least, I think the most important one is for scalability. So if you are writing an application that's actually running on a server, like an ASP.NET application or something like that, then using excessive amount of threads is actually wasting your resources. And if you are using asynchronous code properly, you are not actually using more threads than necessary. That means that you are not wasting any resources, and your application can handle more load with less hardware. So somebody might say the asynchronous operations are something new. It's a fresh new stuff in a C# in the .NET, but that's actually not true, because the asynchronous operations existed in the .NET since basically the beginning. And you might remember seeing methods like begin read, end read, or begin write, end write on, for example, the file stream. So if you are reading something from the stream, from the file, you usually call like a read method that takes 3 parameters. But if you've been looking through the IntelliSense, you can see there's actually begin read and end read method. So that was the first evolution of this one, and it's called asynchronous programming model on APM. There was, and I'm saying there was another one that was called EAP, that was event-based asynchronous programming, that's basically non-existing anymore. And the async await it's not about creating an asynchronous stuff or asynchronous methods from nothing. It's basically a help from a compiler to compose and consume asynchronous methods, because on the bottom, it's always the same. In the in the Windows, in the operating system, there's only one way to do asynchronous operations, or in fact, in Windows, in kernel, it's not called asynchronous operation, it's called overlapped operations, because, I don't know, in 90s, they called it overlapped because it was more about having more operations running like a little bit this one, a little bit that one, and not having a parallelism or something like that, because it's 90s, right? You have one CPU and you have a very slow network and very slow disks or something like that. So let's jump immediately into how thinking about it differs. So let's imagine that you have something like this. You have a method that's called load something. The method creates a list of something, and imagine it's an ID. So from ID 1 to ID 5, it loads something from network. It might be database, it might be disk, it might be network, it might be database, which might be local, it might be network or something like that. Basically something that's not your algorithm. It might be the database, that's probably the most common use case nowadays, or some REST API call or something like that. So you will put it into the loop, you load something from the network, you put it back into the list using result.add, and then you return the list. So everything is okay. You measure it, and let's suppose that you are actually calling some API, and it takes 100 milliseconds to get the response back. So because we have 5 operations to do, you will get the response back in 500 milliseconds. So far, so good. But you say, that's kind of slow. I want to do it faster. Or maybe you don't have 5 operations, but you have 50 operations, and you are thinking, that's kind of slow. I need to get the data from the database or from the API faster. So what I'm gonna do? So because it's a for loop, if you look at the code, it's a for loop. So nowadays everything is about more cores, more parallelism. So you will say, okay, well, how do I parallelize this loop? And probably the first answer you will find in documentation or somewhere on Stack Overflow or something like that, it will be like, use parallel for. So you will use the parallel for, and it will be an easy swap in the code. And you measure how long it takes with parallel for. And let's suppose for this picture, we have 2 CPUs. So one CPU will be doing the work 1, 3, and 5, and the other CPU will be doing the work 2 and the work 4. So you measure the total time, and it will be 300 milliseconds. So that's an improvement. It was 500 milliseconds before, but now it's 300 milliseconds. So that's definitely an improvement. But if you think about it, you are actually bound or limited by the number of CPUs you have, which is kind of weird because you are loading something from the network. The code was actually loading something from the network. So how is that even possible? How does it make sense that you are loading something from the network and you are limited by the number of CPUs? Shouldn't be like the network throughput or the latency or something like that? Well, the reason is that we are actually looking at the method as a one black box, and it's actually not. What it is that at the beginning you have a start of operation 1, then there's a like blank space that you're actually waiting for the database or the server on the other side to respond, and then you get the result back and you process it somehow, and then you start the second one, and then the third one, and so on and so on. And if you draw the picture in this way, you can actually slightly reorder the pieces and do this. So you start the first one, the second one, the third one, the fourth one, and the fifth one, and then you will wait for the database or the other server to respond. And sooner or later, you will get the response back, and you will get it maybe in a different order, maybe between 5 and 1. There will be a slight delay because of some network hiccup or something, but you will get the responses back eventually, hopefully. And if you measure this one, you are basically limited by the longest operation. So if one operation takes 110 milliseconds, the whole response for all 5 will be 110 milliseconds. And if you think about it a little bit more, you will realize, okay, now I'm actually limited by something that I'm actively using. So if I instead of 5, send 50 operations, and the server on the other side will be overloaded and start sending me the responses slower instead of in the same speed, then I'm actually limited by some remote resource, maybe the database or the API server. Or if it's a huge response, like if it's not a, I don't know, like a small JSON, if it's a huge JSON with a lot of data, you might be limited by the throughput of your network. And it makes sense because you've sent, instead of 1, you've sent 5 or 50 requests, and you are getting a bunch of megabytes, gigabytes data back through the network, and you are limited by the throughput. So that kind of makes sense. I'm doing a network operation, and the network or something after the network or behind the network, the remote server is actually my limiting factor, not my CPU or anything like that. So that's fine. It kind of makes sense. But what it means for us? Well, the problem is that we have 2 kinds of operations that we can kind of parallelize or think about. The first one is CPU bound operation. That's basically limited by the number of CPUs we have and by the quality of or fastness of CPUs we have. And these operations are represented by like parallel for or task run, or basically a simple thread. But the IO bound operation, that's a real async code, or only a real async code, because there's nothing you can do to make the operation faster, you know? If you are sending the request with ID 5 to the server, there is nothing you can do in your code to make it faster. If the server on the other side is slow because it's processing a lot of requests, or because your request is like difficult to process, true for ID, probably not, but you can imagine, there's nothing you can do. Your code is just give me the ID 5 and that's it. You cannot make it simpler. You cannot make it the other way. It's just call the server, give it the ID, get the response back. There's nothing else you can do. It's just this. So that's the biggest difference between like CPU bound, where it makes sense to have more CPUs and parallelize it more. While for the IO bound operations, you want to have an async or sometimes also non-blocking code, because if you are blocking threads, it's bad for the system. The system will try to handle the situation, but you will not definitely get the fastest response back or fastest throughput available. And at the end of my presentation, I will show you a simple code, very simple code, and we will see how fast or how slow we will be processing the request when we are blocking the threads, and how the system actually responds when it detects, okay, some thread is being blocked. And by blocked, I mean, it's not doing anything useful. It's basically waiting for the data come back from the server or from the database to respond or something like that. It's basically stopped and waiting for something. So let's jump into like the mistakes or misconceptions with task and with asynchronous code. So a lot of times the people think that the async method runs on something, that there is something that's running some kind of code. So it might be a thread. If you've been digging a little bit into this, you might say it's a thread pool or something like that. And you can answer the question yourself. Is the async method running on a thread or on a thread pool? Is it true or false? Well, on a slide, you can actually see the answer, and the answer is false in both cases. Why? Because of the scalability. When the async method is running, there is no thread being consumed, because you are actually not running any code. So the asynchronous operations are performed by the hardware and then the IO completion port. So if you've been digging a little bit into like Win32 API, you've probably seen the IO completion ports. And while the async operation is in flight, while you are waiting for the server to respond, you are not blocking, or you don't have to block any thread. That means that you can do more with less resources, and you can scale more and all that stuff. So there's no thread being blocked. And I know this sounds kind of weird that you are actually running something and it's not consuming any resources, but trust me, it's like this. It's a little bit more difficult to explain it in 60 minutes. But we will see, at least in the code, that it can behave like, okay, there is no other extra resource being consumed. So the first like optimization you can do, or for first speed up you can do, is that sometimes you have an async method, like add async in my example. And the add async method might be actually doing something really simple, like doing A plus B. It might be an interface, and the interface you are implementing dictates you that you need to have an asynchronous one, but your implementation is using like some local stuff. It might be like, get me the data from the database, but your interface or your code is actually caching the data locally. So you have the data immediately available. You don't have to do the database call and do the asynchronous stuff. So if you have something that's known in advance, you don't have to actually do the task run as in the first example. It's going to work, there is nothing wrong with it, but you are basically spinning a task. The task will eventually consume a thread from the thread pool. Then it will do A plus B, which is really simple operation, and then you will get the result back. So there's a lot of orchestration for doing A plus B. The faster one, the easier one is doing Task.From Result, which means that you will just get the result, and there's nothing wrong in doing A plus B on the current thread. So even if it's a UI thread or something like that, the A plus B is so fast that the application basically can't freeze. So the user will never see that there's any blocking or anything like that, because it's a simple operation. So if you have a simple operation, or you have the data that you already have, like from a cache or something, instead of spinning a task and returning the task or awaiting the task, you can immediately use Task.From Result, and you will save yourself a lot of orchestration that happens when the task starts and runs and gets the result back. You can even improve it if you have something that you know might happen like locally, and that's a value task. Value task is relatively new, but not brand new in the .NET world. And as the name suggests, the value task is actually a value type, which means it's not a reference type as a task, which would be allocated on the heap. It can be returned directly from the method. So there's less allocations, and less allocations means at the end of the day, less work for the garbage collector. So again, you will get a little bit faster, a little bit more responsive application for yourself. So another stuff that happens quite often is long-running operations. So you have a long-running operation like some kind of background processing. Usually it's kind of a sleep-wake type of operation, which means once every minute you wake up, or your code wakes up, does something, and that goes into sleep again. And this happens every minute, every 5 minutes or something. So you might say, okay, I will use task because, well, it's the easiest one to do it. That kind of makes sense. The only problem is that the tasks are executed by default in the thread pool. And when the thread pool is being blocked, and I blocked, I mean, it's sleeping for next, I don't know, like 55 seconds or 59 seconds if it's really fast operation, only for 1 second or something. Then for 55, 59 seconds, you are blocking a thread, doing nothing, just sleeping, but it still needs to be there. The system needs to know about this thread, needs to kind of think about it and all this stuff. And the thread pool will eventually realize, okay, there's one thread that's actually like being used, but doing nothing. So I will do an operation that's called injection, thread injection, that will put an extra thread into the thread pool. And the thread pool by default is keeping the same number of threads as the CPUs. Why is that? That's pretty simple. If you have 5 operations and you have 5 CPUs, there is nothing to shuffle around. You will just put the first operation on the first CPU, the second operation on the second CPU, and so on. And there is nothing to worry about. But if you have like 50 operations and you have only 5 CPUs, then obviously you need to shuffle these around. That's the same with the threads. If you have 4 threads and you have 4 CPUs, then it's pretty easy, right? Because you have 4 threads and you have 4 CPUs. But if you have like 50 threads and only 4 CPUs, then the operating system needs to kind of jump between these 50 threads and give each and every thread a little bit of time, so-called quantum or time slice to run. So the end user, or you as a developer, you have a feeling that all threads are running together while only 4 are running and the rest is being switched back and forth. That's why it's also called context switching. So that's not a solution. It will work because the system is trying really hard to fix it, but doesn't make it any good. So again, you can do the task, and if you look around the task, you might find task creation options enum, and there's one option in this enum that's called long running. You would say, okay, I have a long running operation. It's running basically like all day. Every minute it wakes up, does something, and goes to the sleep. And what this option does is basically it creates an extra thread. That's basically the same as the thread pool injecting a new thread, but only in this case you are creating the new thread immediately. Probably even the worst case is that when you first await this task, the thread will be destroyed when you get the result. So you will pay the price for the thread, because creating and destroying the thread takes some resources from the system. It's a little bit worse than the thread pool. So this is an example. You have a blocking collection. That's a normal .NET class, and you have an enqueue method that puts an extra message into the message queue, and then you have the process queue long running operation, and you basically call it in the first method in the task run, and that's fine, right? The problem is that you will be consuming the thread and blocking the thread and something like that. The better way to do it is actually to start a new thread. I know it doesn't make much sense because I said that blocking the thread is bad. That's true, but you don't have any other option. You would have to restructure your code and do it differently. But if you can, because the API or something like that, your library, then the best way to do it is to start new thread yourself manually. Use the thread for as long as you can. Set is background through, which is important, because if your application is closing, you don't have to worry about closing this thread, because if it's a background thread, it will be closed automatically with the application, and the rest of the code is the same. There is nothing different in the rest of the code. So another misconception or another confusion is the await task the same as task.wait? No, it's not. Doing .wait means it's blocking. It's waiting for the completion. While if you're using await something, the code basically jumps back to the caller, and the caller can do whatever it wants, and then it jumps back into the code as soon as the operation is completed. And it's basically a bunch of continuations, bunch of something that's called coroutines. That's a concept that you've maybe heard of. So it's not the same. It's actually quite different. So you cannot replace task.wait with await task and wait and vice versa. It's quite a different code, and especially with the blocking, it's bad. So oftentimes you can see the task result and the task wait being used somewhere. It's called sometimes sync over async. So you are creating synchronous operation over asynchronous. That's not a good way to do it. It's better to call the synchronous API directly if it exists, and it probably should exist. Because if you do this, if you call task.wait, it can use up to two extra threads. What I mean, the first thread will be the one that's being blocked. The other one is then processing the callback, and because of the thread pool starvation, because the thread pool detects, okay, there is one thread that's being blocked, it might actually inject a new thread. So you will actually consume one thread directly and one thread indirectly. And what's worse, you can get a deadlock if you are using the synchronization context. So that means if you are in the, for example, in the WinForms or WPF application, which this application have synchronization context, then you can actually end up in a deadlock situation. So basically, don't invent stuff. Do not try to invent some way to call the asynchronous operation synchronously, because it's going to end up very badly. And again, we will see how it behaves badly in the code in a few minutes. So that means that the async must be basically everywhere. You cannot stop somewhere in the middle and say, okay, it will be asynchronous from this point below, and it will be synchronous from this point up. Why? Well, you might say, well, my library is fully asynchronous, but I want to provide some helper methods, some easier methods for my users to call. And so from this point on up, it will be synchronous. That's not going to work. It's going to fail badly. But still, people try to do this. So the obvious one is the first example here that you will call just .result, and you will return something. That's not going to work. If you can, use the await, and if you can't, don't even try to do asynchronous stuff. Just use await everywhere. Do not stop somewhere in the middle. So in the second example, this do something async method is basically using await, call dependency async, and then doing the result +1 or something like that. So everywhere, don't cut corners. So that doesn't mean that the people will not try to do any kind of fancy blocking and try to outsmart the infrastructure in the .NET or in the C# compiler. The first one you might do is the example that's on the slide right now. So you want to do the blocking operation, and you say, okay, I will find a way to do it correctly. There must be a way. So let's try. The first one is task run. You will do the async operation inside the task run, and then you call the result. Sorry, that was too fast. So this one is obviously not correct because it blocks the thread that enters the do operation blocking method because you are waiting on the .result. The do async operation will be scheduled on the default task scheduler. So you will remove the risk of deadlocking because there will be no synchronization context. So you solved something, but in the case of an exception, the method will actually throw an aggregate exception where the original exception will be wrapped because it's a task and not an await, and you are calling the result. So that's not a good solution. Definitely not because blocking of the thread. So let's try something else. You will do the task run and do the same do async operation, and then you will call getAwaiter getResult. So it's a slightly different way. Instead of calling .result directly, you will call getAwaiter getResult because you've seen it somewhere or something like that. This still blocks the thread that enters. That means, okay, it's blocking the thread. Something bad might happen. But the do async operation will be scheduled on the default task scheduler. So you will actually remove the risk of deadlocking. This one solved you the aggregate exception problem. This one will throw an exception, the same exception that was thrown inside the do async operation. So it will not be aggregate exception, but you are still blocking. A little bit better, but not the best. So let's try something else. So we can actually do .result inside and .result outside. So this one obviously blocks the thread that enters. Every method will block the thread that enters. But this one is also blocking the thread inside the thread pool. So you're actually blocking two threads. And again, you will get, in case of an exception, the aggregate exception. In this case, you will get aggregate exception inside aggregate exception. And inside the inner aggregate exception, you will get the original exception. So it's a little bit of like exception inside exception inside exception, so on. So that's, I would say, even worse than it was before. So let's try again. We know that the getAwaiter getResult helped a little bit, so we can improve. So we will do the do async operation, and then we will call getAwaiter getResult inside the task run, and the same call outside the task run, the one that we saw in the example number 2. This one is kind of okay because it only blocks and blocks the thread that enters. That makes sense. That's the one. That's the result we want to do. But this one also blocks the thread pool thread. So probably you will be blocking and injecting threads into the thread pool. That's not the best way to do it. So we are probably overthinking this. Let's do something simpler. So we can do async operation .result. We don't need the task run or anything like it. Just call .result because the async operations are returning the task, and you can call the result on the task. So this one is blocking the thread that enters. That's still the same and always will be. The problem is that in this case, you are not having any solution for the synchronization context. So you can actually end up in a deadlocked state in case of like a WinForms application or anything like that. And the same in case of an exception, you will get the aggregate exception and the exception will be inside this one. It doesn't seem like a huge issue, but if you would wrap this one into like try catch block, and you don't think, okay, I need to catch an aggregate exception instead of, I don't know, like index out of range exception or something, then your catch block is basically useless because it's never going to catch the index out of range exception because it will be always an aggregate exception. So like your fellow developers, somebody who is using your library might be actually confused, like why I'm getting this exception and not the correct one, like index out of range or argument null exception or something like that. So okay, backtrack a little bit. That was like too aggressive. Maybe we can do get await or get result immediately on the async operation. So this one again is blocking the thread that enters. That makes sense. The problem is that again you are not making any effort to mitigate the problem with the synchronization context and possible deadlocking. You basically solved only the exception issue. So not an improvement at all. So let's try something else. So let's do async operation, assign the task back to the variable call.wait, and then call get await or get result. So that's just a really confusing code that's doing the same. We've already seen, I think it was example number 4 or something like that. So you are blocking the thread. That's again the same story, but you don't have any effort to handle the synchronization context and the possible deadlocking. You are only handling the exception and nothing specific is done to do extra stuff. So what does that mean? That means that if you are blocking in your code, it's bad. No matter what you will do, what kind of crazy stuff you will invent with the task run and get await and get wait, and you will wrap left and right, it's still bad. There is nothing that's going to prevent your code to eventually like throwing wrong exceptions, being deadlocked in some way or the other. And just because it works now doesn't mean it's going to work forever. So basically what you have to do is have async everywhere. There is no other way to have a good solution for this one. So once you start doing async, do async everywhere. Don't try to invent any shortcuts or anything like that, because you need to have async everywhere. If you don't do that, it's very dangerous environment, and you can quickly end up in a deadlock or something like that. And it's difficult to analyze it. It might be a temporary solution or something like that. Basically async everywhere. But you might say, okay, well, it's nice what you are saying, but how can I do, for example, async in a constructor? I cannot have an asynchronous constructor. So what I'm gonna do now? Show us something, right? Well, it's pretty easy. It's true that in constructor you cannot do anything asynchronous. The constructor is basically given. There is no await, nothing like that. So you need to be a little bit creative. And the one way to do it is basically a factory. I know it's weird and sometimes it could be difficult, but you basically say, okay, I need to create some object and I need to create asynchronously. So I create a factory for it, because a factory is just a simple method on some class or something. So my code on the top with the constructor is basically saying, well, connection factory dot connect async dot result, and it's going to block and throw exception and aggregate exception and all this stuff. What I can do is create a public static method called like create async or something like that. Like create is probably the easiest name to remember, and you will create the service and call await inside it. It's fine. It's a normal method, and whoever wants to have instance of your service, instead of calling the constructor, will call this factory method. Simple. As with everything in the computer science, a lot of problems can be solved with extra level of indirection. And this is extra level of indirection or extra level of abstraction. One thing you might say, okay, well, I can probably do something like continue with, because this method is on the task since the beginning, and I can avoid having the await, because the await kind of forces me to use a newer compiler. Yeah, the await is here for probably, I don't know, like 6, 7 years, 5 years, I don't know. But still, it might be something that you want to prevent, or I don't know. So you will say, okay, I will use the continue with. And strictly speaking, there is nothing wrong with using the continue with. The problem is that the await by default uses the synchronization context. So in case of ASP.NET, it will capture correctly the HTTP context, and I'm talking about ASP.NET in the big .NET framework, not in the .NET Framework core. There's a little bit difference. Or if you are using the WinForms or WPF, it will handle it correctly. With the continue with, you are left on your own, and you need to handle if you are like changing a button or label or text or something in the form. You are left to yourself to do all the synchronization between threads yourself. But strictly speaking, it's correct. There's nothing preventing you to do that. The problem or the drawback is that the await is, I think, simpler and more readable than the continue with, but it's still correct. Now we are getting into like more difficult stuff. So you probably need to have a little bit of experience with the asynchronous operations or something. But still, even if you have a little bit more experience, there are still some hidden corners that behave slightly differently than you would expect. So if you are using the task completion source, and I'm not going to dig too much into the task completion source, but basically if you want to create your own asynchronous operations from other types of asynchronous methods, then you will use probably the task completion source. That's like the building block for all the asynchronous operations you want to create manually. The problem is that if you call the set something like set result, set exception, or set canceled, depending on how your operation ended, it runs in line, and it's not immediately clear that it runs in line. So if I call in my code on the set result on the line that's the second to last, it runs in line in the same thread or something, and it might take some time. There might be some reentrances, some deadlocks, and possibly other stuff. So you should probably always call run continuations asynchronously with the task completion source. That means all the continuations that are scheduled with the task will run asynchronously, will run in some extra thread pool or something like that, and it will not run in line. The other stuff that's quite often missing is that you forgot to pass the cancellation token. The problem is that oftentimes the cancellation token is optional, so you don't actually have to pass it. But it's kind of a mistake, because if you want to then cancel something in your pipeline, you have a lot of async methods, a chain of async methods, and you want to cancel them, and the cancellation token is missing somewhere, then it will not behave as you would expect. So, for example, the read async method on the stream can take the normal 3 parameters. So the buffer, the start, and the length of the operation you want to, or the length of the data you want to read. But it's a good practice to pass the cancellation token. So for example, here in the first method do async thing, I have a cancellation token, and I'm using the default as a default value. So that's okay, because if the user does not have a cancellation token or something, the user does not have to provide it, or the developer doesn't have to provide it, but you should pass it through all your calls. So my second method on the bottom of the screen is actually passing the cancellation token into the read async method. And there's nothing like telling you, hey, you forgot something, or this one, because there is a default one. So once you start calling the async method, don't forget to always pass the cancellation token if you have it, even if you don't plan using it or something like that, because you cannot cancel or you are not expecting to cancel. Just pass it, because in the future the requirements might change, and then the code is just going to work, and you will not have like a hidden stuff saying like, okay, I pressed the cancel button, it's canceling via the cancellation token, and it's still running. Why it's still running? So that's it. I see something probably in the chat. Okay, I will respond that. Cancellation token default is null. Yes, the cancellation token. Sorry, no, it's not null. It's a structure. So it has a default value of something. It's actually cancellation token empty or cancellation token none. I'm not sure whether it's called empty or none, but because it's a structure, it's not null. It's something that you can actually use in further calls. So timer queue, another stuff that can bite you later. So if I go quickly, what a timer queue is, basically each CPU core has a timer queue in .NET, and it's linked list of normal timers. And whenever there's a callback from the timer, like you say, okay, I want this operation to happen every 20 seconds or something, and you are using the timer, the callbacks are running on a thread pool. The problem is that the timer queue is using a lock whenever it's manipulating with this linked list. And if you dispose the timer, it removes it from the timer queue. If you don't, it will stay there. It might not be like ticking, but it will just stay there basically like forever. Well, garbage collector will solve it eventually, but it will stay there for longer than necessary. So sorry for this code, it's a little bit compressed, so I can put it into one slide. But what this one is doing is basically calling the get async on HTTP client and passing the cancellation token. And the cancellation token is created here, and it says, oops, and it says cancel the operation after 10 seconds. And you might say, okay, this is fine. The problem is that the cancellation token source, which is actually a class, is disposable. And if you don't dispose it, the timer that's waiting for the 10 seconds to click will stay there like forever, or it will stay longer in case the get async operation completed successfully. In case it times out, the timer was actually like clicked, and then it can be disposed and everything because it clicked. But if the operation completes faster than in 10 seconds, the cancellation is not going to happen, and it will stay there for longer than necessary. That means it will be there like dangling. And if you are processing a lot of like incoming or outgoing requests, you need to have like 50 operations, then you might have a lot of dangling timers in the queue, in the timer queue, just waiting to expire, especially if you have like not maybe 10 seconds, but maybe 20 seconds, 1 minute timeout. Then for 1 minute, the timer will be there waiting for something. So whenever you are using the cancellation token with some kind of timeout, don't forget to dispose it when you don't need it. So you can actually, when you get the response back, you can dispose it. That's this using block that I have here. It's closed here, and then it will dispose it, and then it will not be in the timer queue on the CPU core. And obviously, the longer the linked list is, the more time it takes also to put a new timer into it. So suddenly your application can become slower and slower. And after like, I don't know, like 60 seconds or something, it might be okay again, because there was a quick load, and then it's okay. So don't forget to dispose it. Another thing that might not be clear is flushing the stream, or flushing the StreamWriter. So you're actually writing into the stream using the async method and everything, and you are using the using block, which is correct. And you know that if you dispose the StreamWriter, it will flush the stuff. But the problem is that the dispose method is synchronous. By default, is synchronous if you are not using await. So that means that the flushing, which often is where the real I/O happens, like sending it through the network or writing it to the disk, because there might be a buffer or something. So you will be actually blocking. So if you are using asynchronous operations, either use asynchronous dispose, which you can use from new versions of the C#, or don't forget to call flush async, like explicitly, manually, before you dispose, so you are absolutely sure that it is flushed to the network or to the disk or something, and you are not blocking in the dispose. This one is another one. You want to have something that happens all the time, and you are pinging something like every second, in my case, basically saying, hey, I am alive or something. And you will start a timer. You will call the heartbeat method, and the heartbeat method is asynchronous, and it's async void. That's not a best way to do it, because nobody is waiting for this method to finish. The better one is to actually await the call that's doing the pinging, that's doing the asynchronous stuff, and just ignore the result. That's what I'm doing in this line. I'm assigning it into the discard, which is a feature in C#. If you don't do this, you will get a warning from the compiler telling you, hey, you are calling do async ping, but doing nothing with the result. So what to do with it? So just assign it into the underscore, which is a special discard value, and the compiler will say, okay, well, you are probably doing something with it, although you are not. With the async void, there is one catch as well. If you have like an interface or a class and you are making it asynchronous, you might have a method like fire and forget that's taking an action. And if you call the fire and forget with the asynchronous method, it will implicitly convert it into the action. But also that means that nobody can actually await it or something do with it. So whenever you are converting something to asynchronous stuff and you have the action, don't forget to add overload that also takes the func of task. Because the action means, hey, it's a method that's not returning anything. But the asynchronous method not returning anything is actually a method that's returning task without any extra type. So don't forget to do this overload, and the compiler, the C# compiler, is smart enough to prefer the one with the task if it's asynchronous lambda, and not the one with the one with the action. And finally, because we are talking about asynchronous stuff and parallel programming and all this stuff, you might be using the concurrent dictionary, maybe as a cache or something. And you might say, okay, well, I want to put something into the cache. But the concurrent dictionary wants to have like an object, like a person or something. So in my case, I have a concurrent dictionary, and it's an integer and person. So let's imagine it's reading it from the database by ID, and I want to cache this object from the database so I don't have to get into the database with every request or something. So let's say I'm using the entity framework, so I will call db people find async with the key, it will be the ID, and because I need to have something to put into the cache, I will call result. And we know that the blocking is bad, so this is probably not the best way to do it. So you might say, okay, well, then I can just call the find async and not call the result and store the task, right? Well, yeah, the problem is that when you get the value from the dictionary, you need to await it, and you will still have somewhere the await, and you don't know whether the value is there or it's still being produced. So the better way to do it, and I understand it's a little bit weird example, but you can definitely put the types into own class kind of wrap-it, is to have dictionary that's actually using lazy of task of person. And what it means is that if I am getting something from the database, it was not in the cache, I will create a new lazy of the task of person, and inside the lazy, I will just call the find async, and then I will get the value. The value itself is the task So that's fine. It will be computed just once, and I can immediately await it, and that's fine because it's being cached. I'm not awaiting multiple times at different tasks or something. I know it's a little bit different, a little bit not different, a little bit weird compared to the first one. The first one was kind of like readable. It's integer and person, while this one is like integer and lazy of task of person. But you can definitely take your own class and wrap the lazy and the task of person into it, and then have a nice type. So like your colleagues or somebody does not have to think about like, what the hell is going on in this code. You will just have a one line with some nice type. So with that, that's everything I have from slides. So I can close this one and I will jump into the code. And I have a simple example to show you like what it means to do blocking, what it means for scaling, and what it means for running the application fine. So I have a simple ASP.NET MVC application. It has actually one controller, and this controller has a hello method that's basically doing a sleep for two seconds, and then it's returning the hello world. The sleep, you can imagine, is like kind of blocking operation. So I'm waiting for the database for 2 seconds to give me the results back. The other one is called sync over async. What it means is that I'm actually having an asynchronous method, but I'm creating a synchronous version. So I'm still returning a string. I'm not returning task. I'm not using any await or async or anything like that. So in this case, I have a task delay that represents for us the database call that takes 2 seconds. And then I'm calling await. Simple as that. And then I have kind of the asynchronous version. So I have the async over sync. So I actually have a blocking version. That's the thread sleep. That's the same as here. But I'm calling task run. So I'm kind of like saying, hey, I'm actually creating an async method because it's a task of string and I can put await, so it needs to be asynchronous. It even says async, right? So it needs to be better. And we will see it's not. And finally, it's the hello async. That's the fully asynchronous world. So I'm using await and the task delay and any task run or anything like that. And again, I return the hello world. Then I have a simple code that actually starts it, and I have a program that's kind of weird. And basically every second, it gives me the number of requests I'm currently processing, number of available threads from the thread pool, number of active threads, which is basically the maximum minus the available, and the minimum and the maximum. We can ignore the minimum and the maximum for now. So we will be interested only the number of requests I'm processing, number of available threads, and number of active threads. So if I start it, and let me do it this way. So I will open another PowerShell window and put it left. This one is right. Let's make it slightly bigger. So what I'm having here is a simple A/B tool that's from Apache web server, from HTTPD, and it's basically A/B means Apache bench, just doing like a benchmark of some websites, and it allows me to send, let's say, 1,000 concurrent requests. So the C means send 1,000 concurrently, and the N means how many requests. So let's say, again, 1,000 requests. So I want to have 1,000 requests and all 1,000 in parallel concurrently. I will use the keep alive on the HTTP, and then I will use, why is not wrapping? Localhost 5,000/hello. I don't know why it's not wrapping for me, but doesn't really matter. So I will start the application. So it's going to compile, and now it says, okay, I'm processing 0 requests and I have 32K available threads. That's the default on .NET Core, and there are 0 threads available. So if I do the hello, so I do 1,000 requests and 1,000, sorry, this is being blocked, and I do 1,000 in parallel, we will see we are not seeing stuff. Is it correctly? Ah, no, actually. It's trying to, what I have, localhost 5000. So let's try again. Now, actually, we see something. So it's 1 request, 2 requests, 3, 3, 4, 4, 5, again 4, 5, 5, 6, 6. So you can see I'm not processing much requests per second, and I'm basically losing available threads. So active is 10, 11, 12, 13, 35, 36. And I'm also eating memory. So if I start the task manager and check the memory, I'm slowly, well, we cannot see it clearly now because it's not eating the memory fast enough, but I'm slowly eating memory. Basically, each thread is eating 1 megabyte of memory. So now I have 56 active threads. So I have 56 times 1 megabyte. So that's not much, but you can imagine if you would have like 1,000 or something, that would be something. So now it completed and gives me the estimation, and I was able to request 16.47 requests per second. That's not much. It could be better, but definitely not much. So what I can do is actually try my hello async. So I will create the async version over the sync version. So it's still synchronous, but I was kind of creating async version over it. So if I start it, we will see that the behavior is basically the same. 1, 1, 4, 11, 12, 13, 14, 25, and 25, still 25, 26, 26. You can see it's not processing much, and we can wait for it to complete, and we will see it's basically the same. I'm not processing like hundreds of requests per second. I'm still processing like 16 or 20 or maybe 25 requests per second. There is not much I'm actually doing. So I'm actually going to kill it and wait for the application to recover. Hopefully it's going to recover quickly. 25, 26, it's still waiting. So that's another drawback you can see, because it's still there, it's still in the queue, it's going to process these requests. And in the meantime, I will do the sync over async. So now it's like, okay, you have the asynchronous version, but for some reason you are doing the synchronous one because you want to have a blocking or something. You want to have simpler environment. So we are still on the 0. Well, not still, we are back to the 0, sorry. And I will start it. And you can see it's still the same. It jumped faster because there was some threads already like pre-warmed. So it started to 57, but still 66, 67, 68, 69, not doing much, right? So I will kill it again. We don't have to wait for it. And I will finally do hello async. So let's wait for this one to recover, or I can actually try to kill it, but it's still hanging there. So I will give it a few seconds and then I will kill it. I will maybe kill it from Task Manager immediately. If I can find it, it's probably this one, .NET Core and the task, and there it is. Awesome. So let's start it again, .NET Run. And awesome, it's running. Now I have 0 requests. I have again 32K of available threads, and I will do hello async. So I have one request being processed, 500, 999, and it's done. And I was able to do 199 requests per second, which is an improvement, but not a huge improvement. The problem is that I was not able to basically have enough requests to do any big load. So I will do 10,000 over 10,000. So let's try again. 666, 2,362, 4,000, 3,000, and we are done. And now I was able to handle 1,068 requests per second. And it was done like in no time. It took a few seconds. What I can do is I can even push it harder, right? Like 20,000. So again, 450, 2,060, 4,007, 4252, Yeah, now it's failing because there was probably too much, but it was processing a lot of requests immediately without waiting for threads to spin or something. And if I freeze it here, can I freeze it? Yes. You can see I'm processing 450 requests and I'm using just one thread, or I'm processing 5,273 requests and just active is 2, because only 2 threads are actually actively doing something. The rest is just waiting for the 2 seconds to happen, and it does not have to block any thread at all. So with that, I will close this. I will close this. I will try to open the chat, and I can maybe stop my share so it's a better one. So Max, hope I read it correctly. Max is asking, like, I have a task run and inside is an async. Is it an async void? How to handle the async lambda? You don't have to actually call the task run with the async lambda. You can await immediately what's there. There's nothing improving your code if you have task run and inside you have a fully asynchronous code. You can just call the asynchronous code, and then if you have maybe some CPU computation, then do that in the task. You don't have to do anything, but it's not an async void. If you have async lambda, you can put it into the method or something, or just put brackets around it and just call await in front of it, and it's going to work. Then from Alex K, or Alex K, probably, sorry, that's not correct pronunciation. It's like English, but probably not, from US or UK. What about next code? Come object, some extension async, await, get some data async. Is it okay to write code like this? Some extensions, it depends. If the some extensions method is properly handling the async lambda, then it's okay to write a code like this. If it's like an action or something, so the asynchronous method is lost in the action, you cannot await it, then no. So it really depends on the some extension method. From Yef and 3 dots, I don't know whether it's the whole name or it's kind of like shortened. Question according to long run. If it's create new thread, is it worse when switching between threads in the thread pool? Probably it depends on solving task. I don't understand the question. So if you can maybe write it differently, or maybe a little piece of code, then I can probably understand it better. Sorry. Then cancellation token default is null. I already answered no. It's not null by default. It's a structure. So that means it's the default value for the cancellation token. It's not null because it's not a reference type. The another one, if async method from a library does not have cancellation token in parameters, but I still want to cancel my loop, then you can cancel. Well, there are 2 options you can have. You can have a timeout. So if the asynchronous method does not return in specified time, you will just forget about it, forget about the result, and start going on. Or if it's like still fast enough, you will just jump out of the loop. It depends how long the async method takes. If it's like a fairly fast HTTP call, you can basically, if the user like clicks the cancel button, it will not be immediate. It will take like few milliseconds, few seconds to actually cancel the operation, and it might be fine. If it's really long running operation that might get stuck for like, I don't know, like tens of seconds or something, then you need to have a timeout. It's called timeout task. If you go into my blog, tabsoverspaces.com, and you will search for timeout, you will find a code, and then you will basically say, okay, I don't care about the result anymore, and you will continue because one of the tasks will finish.
Jiří, just a second about the previous question. Johan asked this question and he is with us, so maybe he'll explain you what you didn't understand.
Okay, awesome.
Thank you for interesting presentation. My question actually about long-running task. What I actually want to know, long-running create new threads. It's not very good thing because it's consumed too much time, and I understand that you would not like to recommend use this option. But if you have several long-running tasks, you and put them into thread pool, it's creates some context switching, and if it's context switching produce some delay between processing some long-running task, and it can be worth than use separate thread and spend some time to create thread on operation system level. And it's a question about you should use long-running carefully, or it's in most cases it's a bad thing and we should avoid it.
The problem is that if you specify the long running, it will start an extra thread, which will take a little bit of time, and there will be definitely some context switching because you are creating an extra thread. But the problem is that if you create it without it and you will use the thread pool will eventually create an extra threads as well, because it will detect, okay, this thread is being blocked. I suppose there is some kind of blocking because we were talking about the blocking. So at the end of the day, you will end up in worst case scenario with the same number of threads and with the same number of context switching. Fair to say the context switch is probably the most optimized piece of code in the Windows or in the Linux kernel. So even though a lot of context switching can hurt the performance, then you might actually think, okay, am I going to write this code in C# and run it in .NET, or am I going to write it in assembly? And it's probably clear that you are not going to write it in assembly because it's a huge overhead to write something like, I don't know, something in assembly, because it would be like a huge task. So all the fractions of nanoseconds you would lose in the context switching, and I suppose you are not creating like thousands of threads, but you will be creating, let's say 20 or something, is still fine compared to other options you have. So the long running is still better than the thread pool, because if you are blocking the thread pool, all the other pieces in your application or in ASP.NET environment will be blocked or will be delayed in the thread pool, because the thread pool is kind of the one place where everything happens. The IO completion callbacks are happening in a thread pool. It's a different kind of thread. It's called IO completion threads, but it's still in the thread pool. And if you are blocking these threads, that means that you will not get a fast enough completion of some asynchronous operation. That's the same with the timer. If you have timer and the timer is ticking, I don't know, like every second, and you are blocking the thread pool, then these ticks, these pings from the timer will be sitting in the queue of the thread pool, waiting for some free thread to process the tick. So you might have like, why is the timer not ticking like fast enough? It's because it's being blocked and it needs to inject new threads. So to sum it up, the context switching, definitely the context switching is something that you want to avoid, but it doesn't matter for normal operations. And for like 20 threads or something like that, it's not going to hurt anything. The context switching becomes an issue when you have like thousands of threads created, or if you have threads that can't run. It's sometimes called thrashing. So basically that means that the system is starting the thread and the thread immediately blocks or immediately says, hey, I cannot do anything. And then the system needs to switch the thread out and start a new one. And the new one says, okay, I can run, and then immediately says, no, there's nothing I can do. And then the system switches to next one. So basically you are spending time like switching between threads doing nothing. because you cannot do anything. But if you do at least something, then it's fine. And if you have like 20 threads extra, it's still okay. Context switching is not going to hurt anything. Does it make sense?
Yeah, thank you for so good and wide answer on my short question. Thank you very much.
Okay, awesome. So the cancellation token, how timer operations are picked up internally. Do systems spin up continuously until this is the current time is a real time to run? No, the system basically, whenever the timer ticks and the next tick is going to be like scheduled, the system computes when the next tick is going to happen. There is like a huge timer queue, and the system basically looks up into the queue and says like, hey, who is next in the next, I don't know, like in next millisecond. And it looks into the queue and says, you and you can like do your ticks. And then it basically says, okay, the rest of the system can do its work. And then again, it picks up what's scheduled for the next interval in the system. Maybe you've seen that the timer resolution in the Windows is like 16 milliseconds. There is a little bit more into it, but let's say it's a 16 milliseconds. And that's basically like the resolution of the timer. So we can simplify and say every 16 milliseconds, the system checks like who is due now and checks it. And then it says, okay, you are due in next second. So I don't care about you. You are due in next 5 minutes. I don't care about you. You are due in next 16 milliseconds. So I do care about you. And in next loop, I will check about you. So that's how it works in high level. What kind of best practice or profile do you use to monitor async IO queue? That's actually a good question. It pretty much depends what I'm trying to debug. If it's a performance issue, I first open, I will share my screen again. How can I do it? Share screen, there it is. I will just open as the first one, the task manager. And in performance, I will open the resource monitor. And in resource monitor, I will just check the disk to see basically who is doing what, how is the disk queue looking. Sometimes I even open the performance counters and see how the disk queue is looking, how many read and write operations is happening. And then I start investigating like what's happening and why. But it pretty much depends on what I'm trying to debug, you know, like, is it an application running slow or is it something being stuck for longer than expected? Obviously, I can take a memory dump from the process, so I can see, okay, there's a huge queue of IO requests, or a huge queue of tasks being like scheduled or something, and that's basically where I start, and then I can like, I don't want to say randomly, but whatever is interesting to me, then I will just start digging into it. There is no recipe I will use to monitor it. But this is basically my like first one. Get the dump, so I can see, is it a lot of IO being scheduled? Why? What is it waiting for? Maybe some log or something, and then check the system, because sometimes it's really it's slow because of the system, because the disk is not able to keep up. The network, if it's a network, then I will check the network utilization, because sometimes it's really the network being fully utilized and there's nothing you can do in your code to make it faster because you are using all the available bandwidth. So next one, thank you for your talk. Awesome. Happy to talk to you. What is the best way to safely cancel a long-running task? I mean, how this task should check the cancellation token to call, yeah. So the cancellation token source, so not the cancellation token, but the cancellation token source allows you to call the cancel method. That will basically set the cancellation token into the cancel mode. And the cancellation token has a method on itself that's called throw if cancellation requested. And this method will basically throw an exception. It will throw an operation cancel exception, and in all the pieces in your code where it's safe to stop the long-running task, like you are not leaving some data corrupted or something, you will just call the throw if cancellation requested. It will throw an exception, and then the rest of the pipeline will basically bubble through with the exception, and that's it. You can call it, basically usually when you want to cancel something, it's a loop or something. So at the beginning of each loop, you can call it. It's really a simple check. There is not much happening because it's a Boolean variable. So it just checks it. It's heavily inline because it's written in a way that it's inline into your code. So there's no extra call, no extra jump. So it's pretty simple to do it. Just call the throw if cancellation requested at the beginning or at the end of the loop, or whenever is possible for you. And you probably know how long each piece of your code takes. So if it's like the beginning of the long-running operation and at the end of the long-running operation, then call the cancellation token. And the second question is, let's say you have the async controller, async action, and it calls some code. Is there any difference if this code is sync or async? Yes, it is. If the code is synchronous and it's blocking, then you will be processing basically less. And I suppose the controller and the action means the controller and the action in the ASP.NET. That means you will be blocking threads and you will be processing more requests per second. We've seen this in my demo. If I called the hello, which was the blocking one, it was the synchronous one with the thread.sleep. It took a little bit, a little while to spin up these extra threads and start processing more and more requests, and it was consuming a little bit of memory. So be async as much as you can. I'm not saying it's always possible, but as much as you can, be async. Sorry, but I don't understand if I need to use async method in filter in Lambda. I suppose I use async, await is element, okay, async. Sorry, Max, I don't understand it. Maybe you can jump on the call and tell me what exactly you mean. You mean like in a where condition, in a link statement or something? I don't know. Sorry.
Yeah, if someone can like explain their questions, you can. Oh, okay. Just a second. Max, you can unmute yourself now.
Yep, thank you for presentation. So I have read about this like async in Lambda, and sometimes it is said that it is compiled into async void when we have such.
Yeah. Okay.
And async void, it is totally bad. So how I should handle it?
Okay, got it. Great. Yes, if you have any method that takes a lambda, basically, then make sure that you have an overload for the function of task and the action. I will share my screen again quickly and show you what I meant in the presentation. It's this one. It's this slide. So whenever you have sorry, I will move my Zoom window. Whenever you have this overload, the compiler will actually take the async lambda and compile it basically into async void, which is bad, as you've said. That's correct. The one way to prevent it is actually to have always an extra overload that takes func of task, and the compiler will prefer this one over the action. And in this one, you have actually a task. You can await it. You can do whatever you want. It's not a void.
So does it mean that when we are using link queue, so we are passing filters in this specific way? So it means that link queue has such implementation inside, because otherwise it means that.
Yes. If you are using the link queue, then you probably don't want to mix together an asynchronous code and the link queue, because the link queue is basically for like CPU bound operation, processing something in the memory. You have like an array or list, you have it in the memory and you want to filter it. So you don't want to mix the async operation and the link queue together. You need to split these into like separate pieces, because for async, you want to have really like async operations, and for link queue, if you want to have it faster or something, you probably want to have like parallel or something like that. Don't mix these two together. That's not a good idea. Okay, so any ideas how to scale the app that uses concurrent dictionary, something task completion source in my case for task coordination? I'm using this structure to achieve synchronous behavior in asynchronous API. Signal are on the server, execute async to the client, and the client calls callback on the server side that does a set result object from this collection. I do await on it. Works fine on a single instance, but not possible on 2 or more. Oh, that's interesting. I would say in this case, it would probably make more sense to completely switch from concurrent dictionary and task completion source and do maybe like actor model, you know, that would make sense, because then you can do this easier. I'm not saying that your approach is wrong. I'm just saying that it might be easier to do it this way. But I don't have an easy answer for you, sorry. But you can send me an email and we can discuss it, because I might probably need a little bit more information of how you are doing stuff that you are doing or something like that. But think about maybe a different approach. I think this one calls probably for like actor model or something like that. DM something, probably Dmitry, right? I don't know, the full name is not here. Thank you for the talk. The question is the following. Are there any pitfalls in removing async await keywords in methods which have only one operation, pass execution for if these methods are invoked in the same way using await, for example? Yes, got it. Yes and no. There is no risk or no pitfall in removing the async await, and it's actually a great way to simplify your code. You just need to make sure that nobody has something around it, like a using block or some logging or something like that. You know, if it's just a one call, like you have in your example, then it's fine. But make sure that nobody puts like some logging at the beginning and at the end, or maybe some using statement or something, because then it's wrong. Other than that, it's absolutely fine, and it's actually a great way to like simplify your code and make it a little bit more performant than doing async await everywhere. Great way. Forward word, it originates from the one and the only David Fowler. Yeah, okay. I will click on it. It's not doing anything. Opening the browser. I will quickly check it. Okay. Send client response, set the result. Okay, task completion source, client, get IP, task. Okay, and I obviously forgot what was the question about. Scale, I'm using this structure to achieve synchronous behavior in asynchronous APIs on server to the client, and the client calls callback. Works fine on the single instance, but won't pursue on 2 or more. Trigger a continuation. Yeah. No, sorry, I don't have an easy answer. Send me an email or something. We can figure it out later, because I probably need to try it in the code. I cannot do it from top of my head. What I'm thinking is that maybe you want to create the task completion source with the run continuations asynchronously. It might be the one, but I need to try it. I don't have immediate answer. Sorry, that's too difficult for me to quickly jump into it. All right. We are actually on time. That's awesome. And no more questions. So if I'm not mistaken, we have 3 gifts or something?
Yeah. We have three gifts. And now we need to choose 3 luckiest ones.
So I would take the last one.